start our class for today. All right, so today we are going to look at, this is a chapter 4, which is we're going to look at optimizing C programming for performance on the embedded systems. So this is the objective of this module, okay, in which you are going to learn how to do a code optimization, okay, in which to optimize the performance of your embedded system. Okay, you're going to look at the code optimization to understand the reason for poor code performance. Okay, so what are the reasons that will result in the code performance, and how to do the power optimization, okay, which is this power optimization is crucial in the embedded system, and introduction to the software tool. Okay, we are going to look at what are the tool available in order to do the optimization and in order to measure the performance of your systems. All right, so let's look at the introduction to performance optimization. So software, okay, recently or nowadays, software has become increasingly complex. Okay, most of the software now is more complex than the previous year. So is the target underlying the embedded system. Okay, so the software developers must be concerned with the performance complex system with a potential of multi-cores. Okay, because now in the today's market there are a lot of multi-core processor out there. So this performance, okay, must consider, okay, the execution time. Okay, what are the execution time? Is it the execution time is faster or slower? And the power utilization. Okay, either it use a high power consumption or low power consumption. So this is the things that we're going to consider in terms of the performance. Okay, so the performance optimization can focus on 3 parts. Okay, we can divide it into 3 parts. The first one here called a single core optimization. Then second one, multi-core optimization. Okay, and the third one is power utilization optimization. Okay, for the single core optimization, so this will be done on the single processor. Okay, if you have a single processor, okay, we're going to look at what are the things that we can do, okay, in order to optimize the single processor. And for the multi-core optimization, so this one here, we are going to look at the processor with a multiple processor. Okay, so this is for the multi-processor. Okay, there are a lot of things. Okay, there are a lot of methods, okay, in order to optimize the multi-core optimization. And last but not least, we are going to look at how to optimize the power utilizations. All right, so let's look at what performance initialization. Okay, so why need and how we are going to perform it. Okay, so performance optimization is the process of modifying a system to amplify its functionality. Okay, you're going to amplify the function of your system. Okay, those make it more efficient and more effective. Okay, so it is a way of acting or producing effectively with a minimum waste, expense, or unnecessary effort. Okay, so this is the reason, okay, why we're going to do the performance optimization. Okay, so why? So due to the competitive advantage, okay, which is the software that run faster and in less space. Okay, so because there are a lot of competitors out there, so you need to have a software that not only can run faster than compared to your competitors, but it also need to have a less memory. Okay, use a less memory space. Okay, and then a part of that, okay, it must have it can increase the possibilities, which is increase the speed, and smaller binary allow for additional functionality. Okay, so this one here again, okay, we are looking at our competitors. Okay, there are a lot of competitors out there. So in order to make sure that your system is above compared to your competitors, okay, you need to make sure that your system can allow additional functionality. Okay, your system have more function compared to your competitors. Okay, and last but not least is get us into the more markets. Okay, so a smaller app can run on a smaller device, because nowadays, okay, when we look around us, okay, more device is much more the device produced nowadays is portable device, which is the device that you can carry along whenever you go. Okay, so that's why you need to have a smaller app that can run on the smaller device. So how we are going to achieve it? Okay, first by using the code optimization. Okay, finding the balance between the code and the small and fast. Okay, because you have a code. Okay, in order to make sure that the code running faster, it faster, and you need to make sure that the code also have a smaller size. Okay, so you need to find the balance between the faster code and the smaller size of the code. And your code must have a better algorithm, which is of course, it must free from any bugs and use assembler at the right place. Okay, because why? Because not all of this programming must use the C programming. Okay, you can embed the C programming with the assembly language as well. Okay, and in order to have a more control to your hardware, because for the assembly language, okay, we can have more control to the hardware compared if you use the what we call it C programming. C programming, you cannot control your hardware, but assembly language is. Okay. Okay, and there are three categories, okay, of performance optimization. Okay, first one here is a single core optimization. Okay, so in this single core optimization, okay, it will give insight into the application and its behavior at the micro architecture level. Okay, later we will see more detail on this, how to do the single core optimization. The second one here, we have the multi-core optimization. So this is involve the multi-processor. Okay, in which you are going to give an insight the execution of application in hyperthreading. Okay, we are going to use the hyperthreading environment and multi-core processing. Okay, there are two methods that you're going to learn. Okay, inside of the multi-core optimization. And for the power utilization, okay, you are going to look at how the application behavior and that impacts the power utilization. Okay, later in the next slide, we are going to look more details on this category, how to do the performance optimizations. So this is the optimization process. Okay, it will start with the design. Okay, you design your system, and then after that you implement your system. Okay, and if there is a debugging debugs in the middle of the implementation, okay, you were going to do the debugging process. If there is a debug here, then you need to fix the debugs. And after that, here, this is where you're going to do the optimization. Okay, there are three types of optimization you can do. First, for the single core processor. The second one here for the multi-core processor. And last but not least is for power optimization. Okay, so now we are going to focus on this part here, okay, for the tuning, okay, how to optimize the process. Okay, so now we are going to look at what is the single core and multi-core overview. Okay, so a single core has just one processor inside of one chip. Okay, see here. Okay, this is your ICs. Okay, you have the integrated circuits. Inside of this integrated circuit, you only have one IC, one CPU. Okay, ataupun one processor, or sometimes we call it as a one core. Okay, so you have one core. But for the multi-core, okay, you have two or more processors inside of single chip. Okay, here you can see here. So this is the multi-core processor, in which inside of this processor here you have four processors: 1, 2, 3, 4. Okay, so this one here we call it as a quad-core processor. Okay, so this is a multi-core. Or if you have a two processors, okay, that one we call it as a dual processors. Okay, and now we have the octa-core processor, and sometimes we have more than 8, 12 processors, 16 processors, and etc. inside of one single chip. Okay, the question here is having more cores better? Okay, so actually having more cores doesn't necessarily means more speed. Okay, but if your app is optimized for multi-core usage, it will run faster with more cores. Means that if your system can fully optimize the multi-core usage, then after that it will run faster. Okay, if not, then the speed is still the same. Okay, example of such apps would be professional music production apps. Okay, that one that can fully utilize the what we call here the multi-core processor here. And then if you have the video editing, okay, so that one also can fully utilize these multi-core processors, and some of the design programming. Okay, some of the design program also can fully utilize the multi-core processor. So in general, if you spend most of your time using an apps that are only optimized for a single core, you probably won't see much benefit from increasing your core count on your CPU. Okay, for example, you have a 4-core processors, but you only use your computer to browse the internet. Okay, so you not fully utilize your multi-core processor. Okay, because that one also can be done using the single core processor. Okay, so now we're looking more details on the single core and multi-core. So a core or a single core is a unit that reads and execute an instruction. Okay, you can see here. Okay, you have this thread here. This is where you read, and this is where after that it execute the instruction. Okay, later on, the manufacturer started to add additional core to the CPU. Okay, first, masa mula-mula, okay, we have the single core processor, but now after that, the manufacturer come up with a multi-core processor, which is it add another processor inside of one chip. Okay, the reason why the manufacturer add the additional core to the CPU is so that the CPU can read and execute more instruction at a time. Okay, you can see here. Now you have a dual core, so you can you can execute 2 threads at one time. Okay, so this will dramatically increase the performance of the CPU. Okay, for example, okay, we are looking at the examples here. Okay, so this is the single core. If you can see here, this is a single core because we only have one core inside of the this chip, and this is a dual core because you have 2 physical core inside of your ICs. Okay, now we are going to run this program here. We are going to run this mathematical equation. Okay, which is 5 multiplied with 4 multiplied with 3 multiplied with 2. Okay, for the single core, okay, untuk single core, what happened here is mula-mula, okay, your CPU will multiply, okay, will do this multiplication first. Okay, which is 5 multiplied with 4, and then it will get the jawapan 20. Okay, so this is the first cycle, And then next, after that, the second cycle, then it needs to multiply with 3. Okay, so it will dapat jawapan 60. And on the third cycles, then after that, it will multiply with these two here, so it will get 100 practice. Okay, so this is for the single core. Okay, which is you need to run one by one lah for this equation here. Okay, and then for the what we call here for the this dual core. Okay, so what happened is because we have two threads here. Okay, you can do the you can run a process. Okay, two process at one time. So what happened here is for this one. Okay, on the first cycle. Okay, the first thread here yang ni akan ambil 5 multiplied by 4, which is jawapannya akan dapat 22. And at the same time, this thread 2 will take the 3 multiplied with 2, and then you get 6. Okay, and on the next cycle, then after that, the CPU will run 20 multiplied with 6, which is you will get 120. Okay, now you can see here. Okay, by using a single core, you need to have 3 cycles to perform this operation here. But if you have the dual core, then you need to have only 2 cycles to perform these operations. Okay, so this is for the single core and multi-core. Okay, the benefit of having more cores inside of your ICs. Okay, and to further increase the performance of the CPU and to make it more faster, the Intel company has introduced the hyper-threading. Okay, now the Intel, it already have the multi-core processor. Now the Intel introduced hyper-threading. Okay, so what is it? So this hyper-threading, technology was added to the CPU. Okay, this technology here was added to the CPU for this CPU for each physical. Okay, so this here we have 2 physical cores here. This is the first core, and this is the second core. And the hyper-threading is used to hyper-threading technology was added to this CPU for each physical core that's on the CPU. Means that each of the CPU have the hyper-threading technologies. Okay, so now what happened here is the operating system will recognize each physical core as a 2 virtual core. Okay, so that's why here you can see here. Okay, so this is the threading, the threads for CPU1. Okay, for example. And this is for the CPU2. Okay, means that inside of this CPU, this physical CPU, okay, the system recognize it as a 2 logical core. Dia ada dalam ni ada 2 logical core. Even though we have a 1 physical CPU, but the system recognize we have 2 core inside here. Okay, sama juga dengan yang ni, the system recognize it as a 2 virtual core inside here. So basically, all right, hyper-threading virtually doubles the amount of core that are on the CPU. Okay, so we have 2 physical CPU. Okay, virtually the hyper-threading double the number of your cores. Okay, that are on the CPU. So this dual core processor will be recognized. Okay, you have the dual core processor. Now it will recognize as having a 4 core through the length of the operating system. Okay, and bear in mind that the hyper-threading doesn't double the physical core. The physical is still 2, but okay, it only double them virtually. Hanya virtually je dia double the number of the core, or we call it as a logically, virtually or logically. Okay, so this is what the hyper-threading do lah. Okay, to double the number of your core virtually and logically. Okay, the number of core is still there, 2, but by using the hyperthreading, it increased it by 2 times. Okay, so that is what the hyperthreading do. Okay, now we are going to look at the optimization process. Okay, so optimized process is an iterative process. Okay, it will keep repeating. Okay, changes during the optimization process may require another round of design, implementation, and debug. Okay, means that every time you do the some changes on your to optimize your process, so you need to do a to redesign, do the implementation again, and do the debugging again. So each proposed change should be evaluated in terms of the stability risk, implementation effort, and performance benefits. Okay, so you need to take these things here, okay, before you doing some of the changes, okay, some of the optimization process. So this is your the things here that you need to take to considerations. Okay, for the single processing, okay, for the single processor, okay, we are going to have the single processing core tuning, okay, which is it will focuses on increasing the performance, okay, such as reduction of execution time. Okay, you can, because you have only one single core, you cannot do the multitasking or okay. So what happened here is we only focus on how to reduce the execution time. Okay, for the multi-core processor, okay, we can do the multi-core tuning, which is focused on the increasing the performance using parallel processing. Okay, now we are going to do the multi-threading, multitasking by using the parallel processing. Okay, kat sini hanya single processing. For the single processing, okay, the target is we need to reduce this single processing so that the execution time is lower. Okay, but here we can reduce the execution time by doing the parallel processing. Okay, and the last one is for the power optimization. Okay, we are going to do a power tuning, which is a focus on reducing the amount of power used in accomplish the same amount of words. Okay, because we know that to if to have the apa ni, if you run to make your system faster, okay, you need to have more power consumption. Okay, so now what happened here is we need to tune that power so that even though the system run faster, but the power is still less than usual. All right, so that is what we're going to do for the power tuning. Okay, now we are going to look at this one here, the single processor core tuning. Okay, for the single core tuning, okay, it only focuses on the single core or single processor where hyperthreading or multi-cores are not considered. Okay, because you have a single core, you doesn't have the hyperthreading, and you doesn't have a multi-core. Okay, so isolate behavior of application from more complicated iteration with other threads or processes on the system. Okay, so can be considered as a serial tuning, and this single core tuning is based on the Pareto principle and Amta Law. Okay, now we are going to look at how to do a single core tuning based on the Pareto principle and Amta Law. Okay, so what is a Pareto principle? Okay, the Pareto principle states that for many outcomes, roughly 80% of consequences are come from 20% of cost. Okay, so this also known as 80-20 rules. So in the programming, okay, 80% of the time spent in application is 20% of the codes. Okay, means that all the effort you put to write your programming, which is up to 80% of the time you do to write the programming, only considered for the 20% of the code. So this observation helps prioritize code optimization effort. So we need to do the code optimization effort because now only 20% of the codes is fully utilized. All right. So this code optimization is most frequently executed portion of the code. So that's why we need to do the prioritize prioritize code optimization. Okay, means that the Pareto principle help you realize that the majority of the result come from the minority of the inputs. Okay, means that this 20% of code must fully utilized, right? So, and for the Amta Law, okay, so Amta Law is actually a formula which measure how much a computation can be speed up by running a part of the program parallelly. Okay, so this is what the Amta Law coming out as, okay, in which the program can be divided into two parts. Okay, the first part here is the program that cannot be parallelized. Okay, there is the part where you cannot parallelize the program, and that is a part that you can parallelize the program. Okay, so program ada dua bahagian. One is cannot be parallelized, and the second one you can parallelize the program. Okay, now we are going to look at what are the execution time. Okay, the total execution time for parallelized and non-parallelized program. Okay, so this is the formula in which T is the total execution time and P is a portion that can be made parallel. Okay, so P here is a portion that can be made parallel. If you have 100% of the program, okay, so what is the portion you can make it parallel? Okay, so this is your program, for example. Okay, this program here, this one cannot parallelize. Okay, you cannot do the parallel. And this one, you can do the parallelize. Okay, so this is the percent. Okay, this is the portion of that can be made parallel. So it denoted by a P. Okay, and meanwhile, T minus P, this one here is a portion that is serial. Okay, this one. Okay, so we have this P. Yang ni adalah kita punya P, and this is T minus P. In which total time here, this is a total execution time, is your T. Okay, your T sama dengan T minus P plus, okay, the total time execution time sama dengan T minus P plus with a P over N. Okay, N is the number of core, or sometimes we call it as a parallelization factor. So this is the equation to get the execution time. Okay, to calculate what is the execution time because of the program or of the task executed, because our program consists of bahagian yang tak boleh parallelize and another bahagian that can be parallelized. Okay. Okay, for examples here. Okay, so this one, okay, yang ni salah yang ni. Tolong tukar, D is actually a P. Okay, and then D is a T minus P. Okay. T minus P and D is a P. Okay, P is a parallelized punya portion and T minus P is a non-parallelized punya section. Okay, so D is a T minus P and D is a P. Okay, so I do the correction dahulu. Okay, and this one is big. Okay, so you have a program. Okay, which is your program here consists of parallelized section, this one, and non-parallelized section, this one. Okay, let's your T, okay, the total time kat sini, from here to here, okay, kita normalize dia kepada 1. Okay, so that's why untuk non-parallelized, the value here is 1 minus P. Okay, so this is where if you don't use any cost lah. Kenapa saya kata tak use the cost? Because P is not divided by your this n here. Okay, let's assume that we have a single core. Okay, kalau single core we put the n with 1 lah. Okay, so this is the equation. You have T sama dengan, okay, we going to find out the execution time. 1 tolak P. Okay, kenapa 1 tolak P? Because I made to normalize the T to 1. Okay, tambah dengan P over N. Okay, so this one here, this is a single core. Okay, if you do a single core, then what happen here is you get your execution time sama dengan 1 lah. Okay, because we already normalize it sama dengan 1. Okay, let's have this N sama dengan 2, which is you using a dual core processor. So what happened here is, okay, you see the execution time now become smaller compared to single core. Okay, if you increase your N, your cores, okay, to 3, okay, so that's why we divided by 3. So what happened here is, all right, your execution time much smaller, lagi kurang daripada when you use the N sama dengan 2. Okay, so here let's we put a contoh lah. Alright, so let's we put a contoh kat sini. Okay, let's your P, okay, contoh the execution time for the parallelization. Okay, let's your P sama dengan 60%. Right? So for the parallelization here is 60% of your T. Okay, and now what happened here? So kat sini tadi kita dapat T sama dengan 1. Okay, now we increase the N sama dengan 2. So what happened here is, by using the formula T sama dengan 1 minus P. Okay, so 1 tolak 60% is 0.6 lah. Okay, 0.6. And then plus with 0.6 divided by 2. Okay, because the parallelization here is 60% of it. We take the P here is 60% of your program. Okay, you're going to it. Okay, so what happened here is, and you will get kat sini 1 tolak 0.6 you get 0.4 plus with 0.3 you will get 0.7. So this is when you use the parallelization factor with 2. Okay, you use a dual core processor. Okay, when you increase the processor by 3, okay, so what happened here is your T, so now we're going to calculate the T sama dengan 1 tolak 0.6. Okay, still same. Tambah 0.6 bahagi dengan 3. Then after that, you will get this 0.4 by plus 0.2, you will get 0.6. Okay, and now you can see here. Okay, so the more number of threads, okay, when you increase the number of threads, okay, so what happened here is the smaller the execution time is. Okay, previously single core you have a 1, and then if you increase the cores here, what happened? The execution time become smaller. Okay, so this is in terms of the execution time. Okay, then now let's look at on the speed up concept in the Amta Law. Okay, so Amta Law coming with this concept here, the speed up. Okay, the speed up of programming of a program using a multi-core, which is a parallel processing, is limited by the time needed for the serial part of the program. Okay, so it given this formula. Okay, so as this is your speed up, okay, equal to 1 over 1 minus P plus P over N. If you recall back, this is your execution time. Yang ni tadi. Okay, the same formula. 1 minus P plus P over N, which is your execution time. Okay, so N is the number of core. P is a portion that can be made parallel, and 1 minus P is the portion that is serial. Okay, the one that you cannot run it parallelly. Okay, so now, okay, we are going to look at what are the relationship between the speed up with the number of cores. Okay, so let's look at these examples. Okay, the execution time of half the program can be accelerated by a factor of 2. Means that, okay, you have a program, okay, and in which P here is equal to 0.5. Okay, half of the program, which is a 50%. Okay, 50% is 0.5 lah. Your P is 0.5. Can be accelerated by factor of 2. Factor of 2 here, this is your parallelization factor, which is N sama dengan dia. N sama dengan 2. So what is the program speed up overall? So now you're going to find out what is the program speed up based on this parallelization factor 2 and the parallelize the P equal to 0.5. Okay, so we put it inside of this formula here. So you will get S sama dengan 1 tolak 0.5 and then tambah dengan 0.5 divided by 2. Okay, because your P is 0.5 and then your N is 2. So now you put here, okay, you put all the values here, then you will get the speed up is 1.33. Okay, so if you not use if you use a single programming, okay, if you use a single core, okay, if you use a dual core, okay, and the speed up of your processor now is increased by 1.33 compared to if you use a single core. Okay, that is the meaning of the speed up. All right, now next, okay, what happened? Okay, if you increase the number of core, okay, now you increase the N equal to 4. Okay, when you increase the N equal to 4, what is your speed up? Can somebody press the calculator? Berapa dapat speed up? Okay, put the ganti yang ni. N sama dengan 4. Anyone? Okay, kamu akan dapat 1.6 betul ya? Alright, you will get 1.6. Okay, next. We increase the cores to hundreds. Okay, what happened? When you increase your core to hundreds, okay, now we increase to 4. Okay, the speed up only 1.6. Okay, compared to if you write it single core. Okay, what happens if you increase the number of core to hundreds? What is your speed up? Okay, 1.98. Thank you. Okay, what happens if you increase more? Okay, you have a very powerful processor. Okay, which is support to up to 1000 N. Okay, what is your speed up? Of course, like this is not this is just the theory lah. Cannot happen in the real world for today's. Okay, so what is your speed up? If you increase the cost to thousands, you will get okay, 2 tu kalau kamu you get 2 2 when you apa tu uh, 2 is it 2 or uh, can you put it in the apa ni dalam bentuk perpuluhan? Okay, no need to run up. Okay, 1.998. Okay, so 1.998. And what happen if you tambah lagi to 10,000 for example? Okay, what is your speed up? I assume that this one here is kalau 1000 is 1.998, so this one should be 1.9998 if not mistaken. Okay, so by looking at this here, okay, no matter how much you increase the number of the processors, okay, which is the number of n here, the speed up values does not increase beyond 2. Okay, you see here, you use 4, the speed up increase to 1.6. If you increase it to 100, okay, it go to 1.98. And if you increase furthermore to 1000, okay, it will the speed up only 1.998. 10,000, 1.9998, which is not beyond 2. So the Amta Law telling that there is a limit to optimization. Not all things you can do. You can do optimization. Okay, there is a limit there. Okay, and if even though you increase the number of core, it will not exceed those limits. So this is what the Amta Law tell us. Okay, so and this is the Amta Law punya graph. Okay, you can see here. Okay, we have 4 graph here. Okay, and for the blue lines color here, okay, so this is where your parallel portion is 15%. Okay, if you put your parallel portion is 50%, okay, so this is your program. Okay, so when your P is 50% and your serial here is non-parallelized here also 50%, okay, and the speed up only up to 2 times only. Okay, the speed up only up to 2 times. Hanya 2 kali je kamu boleh buat speed up. Okay, this you can increase the speed up to 2 times. Okay, when you increase, okay, the portion of the parallel portion here to 75, okay, the red color here. So what happened here is, okay, the speed up only up to 4 times. Okay, means that even though you increase the number of processor, okay, to 65,536, okay, the speed up only up to 4 times only. Okay, and when you increase the parallel portion to 90%, contohnya 90%, okay, something like this. Okay, 90% you do it parallel, while 10% you do it serial. So what happened here is, okay, your speed up is up to 10 times only. And when you increase your parallel portion to 95%, which is this green color here, the speed up, okay, can increase up to 20 times only. And then after that, it will tak boleh lebih daripada itulah, even though you increase your what we call here, your processor. Okay, so this is what the Amta Law told us. Okay, that is a limit to every optimization process. Okay, so I think sampai sini dulu. Okay, before that, okay, we continue with this one, and then after that we stop. Okay, so this is the step for the single core tuning, because previously we looking at the single core tuning. First, we need to do the benchmark lah. Okay, develop a benchmark that represent the typical application usage, And then second one, you need to do your profile. Okay, so this one here, this profile here, you need to do analyze and understand the architecture of your program. Okay, you need to do analysis. You need to do to analyze your program and understand what are the architecture of the program that you use. And then after that, we come up with a compiler optimization. Okay, this is by using an aggressive optimization if possible. And then we go to the general micro architecture tuning. So this is based on the tune upon insight from the general performance analysis statistic, okay, by using the CPI, retired, and so on. And last but not least is specific processor tuning. This tuning based on the processor, okay, contoh Intel Atom based on the non-processor performance issue, which is overclocked. Okay, so this is the step for the single core tuning. Okay, any question up until? Okay, we stop here. In the next class, we continue with a multi-core tuning. Okay, if no question, I think we stop here and see you in the next class.